So in section 9.2, we're going to take it a step further, and we're actually going to find the equation for a linear regression line by hand. The handy thing about this is that all of the numbers we need, we've already found in that table for finding the the correlation coefficient. So if the correlation is significant, the next step is going to be to find the regression line equation. Okay, so let's look at just a real basic scatter plot and line of best fit so that I can talk to you about the process here. So let's say we've got a line of best fit like this, and we've got data values that are not exactly on the line, but they are close to the line. Then what we see from our regression, our linear regression model, is that this right here that's on the line is our predicted y value that would go along with this data value right here. So this is our predicted y value based on the model, but the one down below is the observed data value, observed y value from the data. So our predicted y value is based on the model, our observed y value is based on the data. And then there's a difference between these two. This little height between these 2 points is what we call a residual. And for the residual, the value of that is the observed y value minus the predicted y value. So that residual D is the observed y value, subtract the predicted y value. And the way that we compute a regression line or a line of best fit, well, it's not the way we're going to compute it, but what it is, regression line or line of best fit, is actually the line for which the sum of the squares of the residuals is the smallest. One way for us to graph our line of best fit is to know that the line of best fit will always pass through x bar, y bar. So this is going to be a point that we can always have on our regression line. Now here's how we find the equation of a regression line. For an independent variable. Independent variable x and a dependent variable y. We're going to use y hat to represent our predicted y value. and that is going to be equal to mx plus b. So we just need to figure out how to find m and how to find b. Sounds simple enough. Well, m is going to be equal to n, which was the sample size, times the sum of x times y, minus the sum of x times the sum of y, divided by n times the sum of x squared minus the sum of x squared. B is going to be found by taking the sum of y divided by n minus m times the sum of x divided by n, or y bar minus m times x bar. So what we're going to do instead of starting a new problem is we're going to finish the example from 9.1. We're going to find the equation there. So I still have this scatter plot, and if I flip back a couple pages, I still have my table. Hopefully you've still got your table, because we're going to need these numbers. So to find the slope, the slope is equal to, n times the sum of x times y. That was my green one. The sum of x times y minus the sum of x times the sum of y and then divide that all by n times the sum of x squared minus the sum of x quantity squared. So I'll be flipping back and forth to my other page here to fill in my formula. So m is going to be n, which was the sample size of 10, times the sum of xy, which was 68173, minus the sum of x times the sum of y. So I'll fill those in. The sum of x was 416, the sum of y was 1512. So 416 times 1512 divided by sample size again, times the sum of x squareds, which was this one, 20,398, minus the sum of x quantity squared. The sum of x was 416. So this is actually quite a bit easier to compute than our correlation coefficient was. So I'm going to do the denominator first. And then I'm going to take the numerator divided by what I get there. So here I've got the denominator of 30,924. Oops, I think I did something wrong. Yep, I have too many ones in there. That's 52,738. So that's approximately 1.705406804. So we'll see, we're going to go out to 4 decimal places when we're finished. So we're going to use for our slope about 1.7054 when we get to writing our equation. And then to find the value for b, b was the sum of y divided by n minus the slope, which we had figured out here, times the sum of x divided by n. So to find the value for b, b will be sum of y, 1512, divided by n, which was 10, minus m, which was 52738 over 30924, times the sum of x, which was 416, also divided by n, which was 10. So we're going to get approximately 1512 divided by 10 minus 52738 over 30924 times 416 over 10. 80.2550766. So our B is approximately 80.2551. Once we know what M and B are, we have the equation for our regression line. So our regression line is going to be y hat equals M, 1.7054, times x plus b, which was 80.2551. Now we can go ahead and graph that on our scatter plot using a y-intercept of 0, 80.2551, and another point on the graph, which is x bar, y bar. So to figure out x bar, y bar, we're going to take the sum of x, which was 416, divided by the number of data values, which was 10, the sum of y, which was 1512, also divided by the number of data values. So that point on our line is 41.6, 151.2. So we're going to put these two ordered pairs on our graph and connect them, and that's going to be our line of best fit. So 0, 80.255, there's my y-intercept, and x bar, y bar is 41.6, 151.2. And then I just connect those 2 points. And that will be my line of best fit. So this is my y-intercept. And this was my point x bar, y bar. Now there are some other questions that we can use to answer, or that we can use our model to answer. So we're going to make some predictions based on our model, and then we're going to figure out our coefficient of determination, which I haven't talked about yet, but I will in a moment. So we are going to make some predictions. So in letter A, if x is 60, so if a person is age 60, what would their blood pressure be? Part B, if a person is age 18, what would you predict their blood pressure is? C, if a person is 90, and D, if a person is 44.5. So for each of these predictions, these are ages, we're going to predict what the blood pressure is based on our model. So we're basically going to substitute in our X value in for that X and then plug and chug. So if a person is 60, we will take 1.7054 times 60 plus 80.2551, and we get a blood pressure of 182.5791. Looking at our data here. One thing we want to be careful of is when we're making predictions, we don't want to make predictions that are outside of our data range. So if you look at our data started at age 16 and ended at age, looks like 70. So we're fine to make a prediction of 18, but when we look at making a prediction of 90, that's outside of our range of data. So this one we're not going to predict because we'll say it's not meaningful because the X value is outside the range of data. But we'll go ahead and predict for 18 and 44.5 because those are both within our range of values. So I can just change my 60 to 18, and that gives me a blood pressure of 110.9523. And again, when my age is 44.5, 1.7054 times 44.5 plus 80.2551 gives me a blood pressure of 156.1454. And we'll come back to the coefficient of determination in a moment. And we'll talk about how to interpret that in context of this problem. So let's take a little bit of notes about coefficient of determination. So here, and then come back to that problem. So there's a thing called coefficient of determination. And its symbol is r squared. And what it means is that r squared percent of the variation in y can be explained by the relationship between x and y. Then what happens is the remaining percent, so the remaining out of 100, so 100 minus r squared, the remaining percent of the variation is going to be due to other factors, such as sampling error or lurking variables or coincidence. Now that r squared is found by taking the explained variation, or what it means is the explained variation divided by the total variation. But the way that we're going to find it is just to take the r value that we had and square it. So it's going to be really simple to calculate, and then we'll use this explanation to interpret it. So for our coefficient of determination in the problem that we just worked on. Remember that our R value was 0.90838622326. So our R squared value is going to be that number squared. So we take 0.90836, whoops, 838, left at 838622326, and we square it, and our coefficient of determination is 0.82516555476. So how do we interpret that? We interpret that by saying that 82.5% of the variation in systolic blood pressure can be explained by the equation that relates age to systolic blood pressure. The remaining 17.5% is due to other factors. I just found the problem that I forgot to tape in. So this is the problem we just did, but we did it with the problem from 9.1. So we constructed a scatter plot already, drew the regression line, which we did once we found the y-intercept and the x bar, y bar. Used the regression equation to predict the value of y, and then we also added in finding the coefficient of determination.